Thank you very much. It's a great pleasure for me to be back in Indonesia, back at ITB. When I came 4 years ago, it was a month before the announcement of our result. And I couldn't tell you what it was. You know, it was embargoed. All I said was that there's some really nice results coming in a month, but I can't tell you. But today I can tell you all about it. What happened in the last 4 years, okay? So this obviously is the picture that everybody has seen, right? It's on all the newspaper. It's the black hole shadow image in the M87 Galaxy. Okay, so I want to tell you about that. Can we turn off the lights because my slides are very dark? First thing is, how do I advance the slide? Okay, so black hole imaging is one of the 3 key experiments in gravity, okay, which I'll tell you about. And Asia has been playing a very important role in this particular experiment to image the black hole. In particular, you have to think about this as your experiment because Indonesia is part of the East Asian Observatory today. So from this point on, when we are working on this project, you should think that Indonesia is involved. And if any of you want to be actually working on a project, you should just come join us. So it's not a big deal. It's easy to do. Actually, it's not very difficult. But in studying gravity, the key is the technique. The technique is, all 3 experiments is about lasers and it's about interferometry. And this image, of course, the most important thing is that it verifies general relativity. Okay, that Einstein was correct in his prediction, and it has many implications on the astronomy that we study. And I want to tell you that Asia is working on the next steps. And how we succeed depends on this collaboration, right, between government, between research organizations like ITB, industry, universities. These are working together in order to make these things happen. So, of course, most of you don't need me to answer this question, right? But it's important to remember the astronomy is very important because we answer the basic question of origin of everything. And we study the largest volume, right? We study all space, because we study all the universe. We study all time, going forward and backward to the beginning of the universe, to the end of the universe. This is our subject matter. It's no wonder that we require a lot of budget, right? More than anybody else, because we are studying the biggest area, biggest volume, biggest time. So we should demand more money. Okay? And furthermore, astronomy is easily understood by the public. Okay? I've been in Malaysia, I've been talking to the amateur astronomy. You know that there's no such thing as a planetarium for biology, right? There's no amateur biology clubs. But there is for astronomy. The reason is everybody understands astronomy is important because from the young age, in all civilization, when we look up in the sky, this is the one thing that always reminds us that we need to understand what is the universe is doing, okay? So for this, it's important for stimulating science, and it's important for driving technology transfer, development, big data science. These are all important in your future. So of course, in 2019, we reported this result on supermassive black hole. It's on all the newspapers, which is impressive. More impressive, of course, is that it was on the Google banner. You know, anything that shows up in Google banner, you know this is important, right? It's only for that day, right? They made the Google banner and they got the whole idea correct, that the black hole is there, it sucks everything in, including the Google banner. And after that, of course, we had some very important prizes were awarded, in particular the Breakthrough Prize in Fundamental Physics, which is one of the big prizes awarded in science. So why is this so important, right? The reason is that the black hole study is a key to the fundamental physics. Okay, you can say something that's invisible now we can see. That is always exciting, right? Things that we couldn't see before, for the first time we can see again. Okay, it's the first time. And then this is examining where gravity is the strongest, right? At the edge of the black hole where the gravity is the strongest that we understand. And it's so strong that there's no escape, as predicted even by general relativity. Even light itself cannot escape from the black hole. That's a concept, right? And then information from inside the black hole cannot come out. There's no information escape. So this mysterious object, of course, on the small scale, we know what they are, right? They are the end state of a massive star, 5 to 10 times the size of the sun. Explodes, the end result, the last result is actually the remnant is the black hole. That's a small black hole. The big black holes, billions of times the sun's mass, is actually found in the center of galaxies. Of course, when you talk about black hole properties, you would like to know what are the properties that defines a black hole. And I want to tell you that that's the main thing is about the mass of the black hole. Okay? That determines what the temperature will be like, what the density will be like, and what the physics will be like. So in this type of study, we are testing general relativity, and I want to tell you the experiment that I want to talk about is an optics problem. Like in physics laboratory, optics where information is missing. So if you're missing information, how do we retrieve the original picture, right? That's a missing information problem. So the physics are relatively easy, not difficult. Escape velocity, you know, just like if you want to send a satellite out, the typical escape velocity from any planet is on the order of tens of kilometers per second, right? You have to achieve tens of kilometers per second in order to escape gravity. What does that mean? It means that the kinetic energy has to be greater than the gravitational energy, right? The binding energy of gravity has to be exceeded in order to stay forward. Now, of course, things are a little bit more complicated because we are actually dealing with relativistic type of things. The escape velocity in the previous slide, V escape, actually we know that the escape velocity cannot exceed c, cannot escape the speed of light. Why is that? It's infinite if you try to drive towards the speed of light. Okay? That's the relativistic factor, gamma over here, right? Has that dependence on speed of light, so that when the speed of light when the speed gets close to the speed of light, that energy blows up to be infinite. So that's why you cannot escape beyond the speed of light, right? So that defines the radius where the maximum velocity is the speed of light. And of course, this is just normal Newtonian type calculation. Actually, you have to go through the general relativity calculation, but it turns out that the number comes out to be the same, 2gm over c squared as the Schwarzschild radius, okay? So two things, special relativity tells you that the speed of light is the limit, and general relativity tells you that even the light have to follow the distortion from gravity. Okay, so this is the test that we are testing, these two, okay? And then, because of this relation, the Schwarzschild radius, the limit where material inside that radius just cannot get out, that tells us what we call a metric, right? A metric means I collect the constant on one side, the other side is the variable, right? It says that you have to satisfy this relationship in order to be inside a black hole, okay? So note the property. The property relation is amount of matter over size, not density, not total mass, but the amount of mass distributed over the linear size of the black hole. That's a very important property. It's the metric. Okay? Now, physics, of course, when you say, what does the physics look like, right? When we think about physics, it's always about density and temperature, okay? So because this metric is defined by m over r, you can see that the density goes as m over r cubed, not m over r, right? The density is a much harder function on the size scale. So that means that if you have a small black hole, let's say the mass of the Earth, that density is fantastically high, 10 to the 27 times. Okay? But if the mass of the black hole is like M87, where the mass is billions of solar mass, the density is very low, 10 to the minus 3 times the water density. Okay? What does that mean? The bigger the black hole, the physics may be more ordinary. What is actually the answer? The answer is, if you calculate this for the universe, you find that the universe mass size comes out to be approximately that of a black hole. So we could be living inside a black hole. Why are things normal then? Because the density is actually low. Okay? Now theoretically, you can't tell from the outside because information cannot come out. But just the density calculation tells you that a very large black hole, things could be normal, like now. Okay? So that's an important point to think about. So, okay, so what did the picture tell us? The important thing the picture tells us is that it's black. Looks like it's a hole. Like it's a black hole. But of course, this is not the black hole itself, right? That's actually the shadow around the black hole. The black hole itself, of course, you cannot see, right? It's invisible. But what we see here is the shadow. What is that shadow caused by? It's actually the light being bent by gravity. So it never gets to us, okay? And the size scale in M87, a very small number, 42 micro arc seconds. It corresponds to where the Voyager satellite has gotten out to in the solar system. So this black hole shadow in M87 is on the order of the solar system. It's not very large. Okay, so the physics, again, it's not very complicated. I just want to tell you, just the freshman physics is enough, right? Things like, well, a spectrum, the energy scales as the wavelength so that the temperature is representative of energy, right? High energy, high temperature. Speed of light is a constant, that's from special relativity. Apparent size of an object that scales with the distance, things that are further away look smaller. That's one of the things that we're testing here. Total energy is conserved, that's the energy conservation theorem, and that actually produces the ring, okay? Why? Because things falling in, conserving the energy, actually settles into that ring structure where the energy is balanced. Angular momentum is important, which means that the stuff actually rotates faster. If you have a little bit of angular momentum, it goes faster, just like a spinning ice skater, right? Ice skater draws the arm in, they spin faster, right? That's because it scales as 1 over r. When you hold the angular momentum constant, and then the Doppler motion of self is very important. This is the whistle effect, of an object that's moving, right? If the object is moving this way, the wavelength is longer in the back and compressed in the front, right? That's why you hear the pitch of the whistle higher as the train is coming, and when the train has passed you, the pitch is lower, right? That's the Doppler effect. What is the importance of that Doppler effect? Actually, that gives us the picture of the ring, why one side is brighter than the other. Okay, so that's also a very simple physics. And then, of course, this special relativity, general relativity creates a shadow, which I already talked about. And the spectrum, here I tell you the spectrum, very important, because normally we are in the optical. The eye is adapted to the sun, so the eye is responding to the sunlight. It's about 6,000 degrees, okay? But the bulk of the universe is extremely cold. The bulk of the universe is about 10 degrees. So if you want to study the galaxy, study stars, you can look at the optical, but the bulk of the matter is actually very cold, right? Temperature scales is the wavelength. So if you want to look at things that are cold, you have to get to the submillimeter. You have to get into the radio, very low, long wavelength. And there, because its temperature is low,
But also now the size scale becomes big, the structures become big because the wavelength is longer. But we work in this particular wavelength just because the sky is transparent enough here that we can see through. Very long wavelength will be blocked by the ionosphere. Shorter wavelength will be blocked by water in the atmosphere. So this turns out to be a sweet spot for us to be working at. And that's why this experiment is done at that wavelength. Okay, so what are the methods for seeing gravity, feeling gravity, and hearing gravity, right? Those are the three ways to test and study gravity. You can hear it, that's the gravitational waves. There's about tens of cases now, okay? You can feel it, that's the attraction of the gravity forces. There's one case, that's the galactic center. And then there's the imaging of the event horizon, two cases, okay? The first two experiments have won the Nobel Prize. Okay? Gravitational wave, motion of the Sagittarius star around the black hole. So the common techniques here is using the lasers and the interferometer, okay? As I told you already. So we are testing general relativity and studying the event horizon. First, I want to tell you about hearing gravitational waves. This is the LIGO experiment. This is the laser interferometer, Gravitational Wave Observatory. Typically hearing the sound of two very compact objects colliding. When they collide, get close, gravitational waves are released, okay, from that interaction. So the signature is detected in these interferometers. They are basically two long arms with mirrors at the end. And when the gravitational wave comes along, a little vibration occurs on the mirrors, and you detect this vibration in both legs on 3 sites. Okay, why 3 sites? You want to detect the same thing so that you know that you're not detecting a bus going by, right? And then you want to detect the signature. What is the signature that tells you it is gravitational waves? This is a very delicate experiment, right? So this very experiment typically is in a very large vacuum tube, kilometers in length, measured distance between the two mirrors, how? With a laser, right? Bouncing the laser back and then checking what is the distance between the mirrors. So it's like a laboratory experiment that you would do in your lab bench, right? It's nothing complicated. Well, it's very complicated because there's a lot of noise in the system. The idea is very simple, you know. You just take the two mirrors, you send the light down, and then you are checking what is the motion in the vibration. You know, you have things to check that. But these are actually typical tabletop optics experiment. Okay? And the signature comes out looking like this. Okay? These are the 3 sites, 3 interferometers. Okay? What you see here is a signal to noise as a function of time. Here's the frequency as a function of time. Here's the distortion in the mirror as a function of time. First thing to note, time is very short. This is 0.02 seconds of time. So the whole thing is done in 2/10 of a second, a very short signature. So you would say, how the heck could I tell in a 2/10 signal that happens only once that that's a gravitational wave? Okay, and that's a theory. The theoretical calculation was already calculated of what the 2 neutron stars colliding would look like, what the ringing pattern should be. Then you measure the strain, and you find it fits the theory. Okay, so if the theoreticians, which I usually dislike because I think theoreticians don't know what they're doing, but in this case they knew what they were doing, they calculated it. Had they not calculated it, we wouldn't know what we heard. Okay? So this tells you in physics, really important that the theoretician and the experimentalist have to work together. Okay? Second thing is the frequency. The frequency is about 100 hertz. That's why I say 100 hertz, of course, is sound, right? That's what your ear would hear. So what you hear here is that the pitch increases, and then it decreases and fades away. Okay? With a ringing pattern, the frequency is shorter, higher frequency, and longer here. It rises and then disappears, rises and disappears. So this signature has been seen now in tens of cases. Okay? They all look like this. Strained sound wave. Okay? So we now have many cases now of these things. And then the question is, where are they? So that's the problem. Even with one single interferometer, the wave could come in any direction, right? It's very difficult to know which way. So you need some triangulation, right? So if you have several, you can start to narrow. So in this particular case, detection was done by 2 interferometers, separation delayed by 10/100th of a second in time. And by that, they can say it's somewhere in here along the galactic plane, Milky Way, it's somewhere in this little box. The box is not so small, right? But when you add these other interferometers, the box will get better. So in the meantime, what do? You have to search quickly on the sky to look for a signature that's consistent with the gravitational wave. So this I show you is also an Asian experiment. This is the Japanese National Telescope on Mauna Kea. This is called the Subaru telescope. But we have this very big camera that we have built, including Taiwan was joining in this effort. And you can get the picture of M31 all at once in one shot, because it has many, many, many detectors all put together, covering a field of view of 1.5 degrees, which is quite large. And from that, you can actually see many galaxy structure. These are actually Einstein ring effects of lensing of galaxies in the background. And also you can see the structure of the galaxies, you can detect them. And with this particular camera, you can do dark matter distribution. Actually we can use the distortion of the picture of the galaxy to deduce that there's dark matter along the way. In other words, we have more mass along the way than what we can see. We have this dark matter, which is actually distorting. So this is a way for us to map the dark matter. This is another story. I just point out that we now can do all sorts of interesting things. But with this very large camera, we can map a very large area swath, and then they found this particular object, which faded on the time scale of days. Okay? Question is this the guy that is the gravitational wave detector, emitter? So again, depends on theory. We can calculate, depending on the model, we call this a kilonova model. In such a case, they can calculate the time profile of what you might see in terms of the light of the source, if this is a neutron star event. And then, you can calculate for the different wavelengths what it will look like, and we fit it across the data, and we find that this is a likely process, likely source for the collision of the neutron stars that give rise to this. So there are several types of things. We can have neutron stars, black hole collision, black hole collision, but these are all relatively small black holes, small neutron stars, a few solar mass type things. But we can study them. So in the future, we will do more, right? Identify the source of gravitational wave. We will increase the sensitivity by building new instruments for gravitational wave detection. And then hopefully, what we would like is to see the very massive black holes collision. And for those, the important things is the in-spiral phase, that is when the thing is coming in and the thing is merged and then it fades. In these information is actually tests of the general relativity effects, higher order effects, will affect how that ringing looks like. Okay? So we are looking for more sensitive tests for this. So what is the backstory of this experiment? This backstory experiment is that in gravitational wave, 2 new Nobel Prizes have been given. The first one is Taylor and Host for binary pulsars that are spinning down, getting closer together, and gravitational wave is emitted. They can calculate, okay? And it's consistent. And this one is Ray Wise, Kipton, and Barry Barish for the gravitational wave experiment. And that's Ray Wise in 1970s, working in his lab on detectors that looks just like the detectors that we're using today, viewers, infrared detectors. Why do I talk about Ray Wise? Because this experiment started in 17 when Einstein predicted quantum theory, okay, of radiation. In 1953, Charlie Towns, remember the name, Charlie Towns? He discovered the mason. which actually is the laser, right? Maser is about microwave, laser is about light, so he invented the laser, okay? So after he invented the laser in 57, in the 60s, he got the Nobel Prize, and then the labs began to be able to use lasers, okay? Those very large lasers. I myself was working on this. I was working on liquid dye laser in this lab. How did I start? Because as a freshman, my professor says, come to evening seminar. I say, why should I come to seminar? I already have classes during the day. And he says, we have donuts. I said, donuts, I'm coming. So I went to the seminar as a freshman, right? The rest of them were professors. I just eat donuts and watch them. In that seminar was Ray Weiss. And he starts to work on lasers, and we're studying what is the next thing to do in physics. So out of this became the gravitational wave experiment, because they thought lasers, the most important use of lasers was to try to do this experiment. Okay? It took 50 years. Okay? I ate donuts. I gave up laboratory physics. I thought astronomy was better. This is how you make decisions. Okay, next, feeling the gravity. Okay, this is about in the galactic center, our own galactic center. There are stars that you can see, and these clever guys, the team in Max Planck in UCLA, was looking at a star around the galactic center region. They find the star is going around in an orbit. There are several stars going around. Okay? But one particular star has an orbit of about 15 years. Okay? The important thing is, when they saw it moving here, a little bit of the arc, they already predicted this was a test for black hole, test for the galactic center black hole. Okay? From this experiment, laser came. This is in European Southern Observatory, very large telescope interferometer. You know, astronomers are not very good at making names, right? Very large telescope interferometer. That's the name. So this is 4 telescopes joined together as an interferometer to make very high images, high resolution images. And again, very careful experiment. I want to tell you that the experiment is very elegant. Okay? We look at the star field. You have to choose one of the stars here for adaptive optics. That means to correct for the sky atmosphere. We are moving the mirror and adjusting in order to get rid of the atmosphere. And then after that, you have to pick another star to check the fringe. That's to measure the interferometer baseline to make sure that they are measured properly so that the image stays stable. Okay? So a series of these things on making this interferometer produces a resolution of 3 times 10 to the minus 3 milli-arcsecond. Okay? The figure of merit, optical telescope, typically a big telescope, you would say resolution, if you have 10 to the minus 1 is pretty good. But they can achieve 10 to the minus 3, and then the relative precision is 40 micro-arcsecond. Remember this number, 40 micro-arcsecond is very accurate. Okay? So with this, another benchtop laser interferometer, which is just laptop, you know, just a desktop type laboratory experiment. And with this, they measure the orbit of this star very accurately. It goes around the black hole here, Sagittarius star, and in particular, the orbit right here, because it's close to the gravitational center, is going to pull on it faster, right? So this pull on it stronger because you're closer. This part will move faster. Okay, so you can measure this distance, this position very accurately. Okay, and with that, they are able to measure the orbit very accurately. So just to tell you, you know, in a matter of days, right, they can actually see the star moving. So this is a very delicate experiment, right? The resolution is extremely small. This is 5 milli-arcsecond, right? So relative position very, very accurate. They can even see the motion of the star when it gets close to the source. Actually, this increase in velocity is a general relativistic effect. It's not just a normal gm over r squared. There's a term due to general relativity, they measure it. Okay? So that's a Nobel Prize. Okay. Next generation experiment will work on very large telescope. Asia is already evolving these telescopes, so I think we will be able to do better things, looking at fainter things, seeing more stars, getting more accurate things. I think many more things for this type of experiment. So what's the background story? Okay, background story, this is Reinhard Genzel, this is Andrea Getz. Genzel worked with this guy, Charlie Towns. Same guy, laser guy, right? He worked at Berkeley. At the time, I was also at Berkeley with Reinhard. Guy in the middle is Fred Lowe, who was our director at IAA, also working on black hole. We were all working on black hole. What's the backstory? 67, Charlie Towns moved to University of California, Berkeley. He made a group starting to study the motion of the galactic center gas. Reinhard Genzel shows up, and he moved from originally doing VLBI to doing infrared astronomy. Me, I moved to submillimeter interferometry. So again, choice. You have to make a choice of what you do in life, right? So he measured this. In a few years, he started to measure this orbit. 10 years working with Towns, begin to measure the orbit. He found in just a few years the beginning of the orbit. Okay? And then that's verified. He built even better experiments, and then Nobel Prize in 2020. Again, 50 years of work. Right? Me, I work on imaging black hole instead. How do you choose what you do, right? At the time, I thought I was doing the right thing and he was doing the wrong thing. I asked him, why are you doing infrared? And he says, I don't know, he says. And I said, well, I'm not doing it. Okay. So Nobel Prize winning work is all about precision. Okay? You have to measure things very, very accurately. So you can see the last two experiments. They are very, very fine measurement. Because of this very high precision, you can get to the fundamental properties, you can get to measure whether constants are correct, whether equations are correct, and that typically you find a very important phenomenon, right? And typically leads to important discoveries. Discoveries typically means new technology. Interestingly, Nobel Prize winners stimulate more Nobel Prize winners. So the answer is go work for somebody with a Nobel Prize, right? If you can work for somebody with a Nobel Prize, maybe you get a Nobel Prize also. Well, only works for one person, right? Out of his many, many students. So the interesting thing is, why does that work? I think working with brilliant people draw brilliant students. That will enhance the future, right? The best people want to work in the best interesting conditions. That is why the professor is very important. Okay? Why do some problems have multiple prize-winning work? It's because the problem is rich. It is not just one topic. It actually has many things that you can ask. That makes the problem rich and important. Okay? So when you're picking work, what to work on, these are things to pay attention to. Okay, now, I'm halfway through. Now I want to get to the final story about taking a picture of the black hole, right? So the key here is that the black hole has a very large mass. It means that the size of the black hole will be small, and then, because it's very far, 53 million light years away, the Schwarzschild radius is only 10 micro arc seconds. Okay? Remember the experiment from Genzel. He is achieving 40 micro arc second. 40 micro arc second relative resolution, milli arc second in absolute resolution. This is going down by another factor of 1,000. Okay? We have to get to very high resolution. Compared to the moon or the sun, which is 30 arc minutes, you can see this is a very small number. The black hole is 10 to the minus 9 the size of the moon, right? It's a very small size. What is happening? Einstein's theory is the gravity actually affects the geometry of space itself. Okay? When you have strong gravity, the space around it is no longer the normal linear Cartesian coordinates. The space is warped. What does space warp means? It means that things have to follow a new geometry. Things that follow a straight line before now goes to a curved line, right? That is the reason why he reasoned light has to be bent, because the geometry itself is distorted. It's a very difficult concept to think about, right? How do you distort space? And so the key here is that instead of the usual way to bend light, which is like in a pyramid, in a prism or between different material or your glasses, these are dielectric type material effect. This is gravity and geometry effect, to bend light. Okay, so this is the general relativistic concept, and he makes specific prediction of how much would the light bend. So the idea is, if you're looking from here, the light is coming around the black hole. Because of the black hole, it begins to bend in. So this light that's bending never come out, right? Never reach you. That's why there's a shadow. The shadow is due to the fact that some part of the light has now been bent into an orbit or into the black hole itself. And then you have a shadow, and general relativity calculates what this size should be, 5 times the Schwarzschild radius. Depending on the mass, you calculate this Schwarzschild radius, it says the shadow has to be that size. That's what we're testing. Is it 5? So, in the galactic center, in our galaxy, in the radio, it's a very splashy radio picture here in the continuum, 90 centimeter wavelength. You get a very splashy thing. These little circles are supernovas. An explosion expands the shell. So we can see many little shells, right? Including in the middle, we also think this is a supernova. I think this is a blow-up picture of the middle. And if you keep blowing it up, you find eventually there's a spiral-like pattern. And there's a little dot over here that we cannot resolve. Okay? At a resolution of this is 8 arcsecond, this is much smaller than an arcsecond. We cannot resolve this object in the radio continuum. Okay, so why do we do it? Of course, seeing is believing, and it turns out that we only have 2 targets that we can work with. Both of these cases turns out of a shadow of about 40 micro arcseconds. That number, 40 micro arcseconds. Right? 5 times the Schwarzschild radius. The Schwarzschild radius is smaller, but then the shadow is the size that the relative accuracy of the Genzel experiment, we actually have to get down there and see the actual resolve that. So to do this, we do very long baseline parameter precision, 1 part 10 to the 10, right? This is how accurate you have to do the experiment. And the idea is, of course, depending on the size, the further it is, the bigger it looks like. A thing that's small, close up, can be smaller, but on the sky will look like the same, right? 1 over r, right? So that's why the galactic center is a much smaller black hole, but actually turns out on the sky has the same size. Okay? There's only 2 that we can work with at the moment. Okay, so in 2017, we have this experiment. Asia actually participated by contributing 3 of these telescopes for the experiment in 2017. And the idea is to pretend to be a very large telescope the size of the Earth. And in order to make a picture, you have to pretend it's a real mirror, right? To pretend it's a real mirror, you have to be accurate to the surface, 1/20th of a wavelength, 40 micron, over a distance of 10,000 kilometers, okay? Over 10,000 kilometers, you have to track your surfaces to that accuracy. So you can see it's a very tight experiment, okay? You have to check measure the distance very carefully, arrival time very carefully, take care of the atmosphere, fix the electronic effects, compensate. Every telescope would be different, and then missing information because we actually have very few telescopes. Okay? But this technique itself received a Nobel Prize in '74 for aperture synthesis, image reconstruction. Okay? So the other source is M87. This one is a picture on Hubble. You can see the optical. Already we knew something very interesting. Here's the galaxy. There's something coming out, right? The thing that's coming out is a jet, a relativistic jet, which we can actually see in the radio. The jet, the galaxy is in here, the jet comes out and then eventually spread out into a very large lobe. But if you look at this at higher and higher resolution, it continues to be a jet until the very end. Here, this is 10 milliarc seconds, still looks like a jet, something in the middle. Theory says a black hole. Okay? Why? Because black hole is the most efficient way to push the energy out. Okay, and we can measure the property of this. You can measure the stellar motion of the stars, just like in the galactic center, and from that you can guess what the mass should be. It's on the order of this, billions of solar masses, but not clear exactly what that is, whether it's 3 or 6, depending on the model of the stars. But the VLBI measurement at other frequencies tell us that the shadow should be on that order, 40 microarc seconds. Okay? So, what we try to do, direct proof that there's a supermassive black hole. When we measure the shadow, we are measuring the metric, and then we test the general relativity. We can calculate mass, we can calculate spin. We actually have astrophysics for the jet coming out, accretion, formation of jets. So that little dot, we want to resolve into something like this. Okay? To do that, we need to improve almost 1 million times in resolution. That's the experiment. So theory says you should see a shadow, but if the thing is actually flowing in a thin disk, maybe you'll see this. Okay? And if the black hole is spinning, you might see this, because light on one side will be better than the other side, stronger, and the shape of the black hole will be different, right? So there's tests, theory, predictions. And then, we do simulation, if the black hole image is like this, with our experiment, what should you see? You should see some ring. That's our prediction before the experiment. And then in 2017, we deployed many teams across the globe to do this experiment. And the experiment is basically one of collecting data. And the way it works is that as the source goes across the Earth, telescopes begin to be able to see, right? Every time 2 telescopes come in, we measure the interference. Every time 2 telescopes appear, we measure the interference. And as this image of the source appears across the Earth, which is actually the Earth rotating underneath, then various telescopes come into play and we can make measurements, okay? And the idea is what we call building up the image. So every time the telescope comes in, we get a data point, and more telescopes come in, more data points, okay? And then the image that we get, depending on how many data points, then when we start out, we go around. First it's blobby and you can't see what was going on, right? But as you add more and more data, eventually the ring comes out, okay? So you have to fill out enough of this. What does this mean? It's like you have a mirror and you broke it and you kept only a few pieces of the mirror. And you say, what does the picture look like? Well, obviously, if you only have 2 pieces of mirror, it'll be hard to figure out what the image looked like, right? But if you can collect more and more pieces of mirror, then you will become better and better picture, right? That's the information. The missing part of the mirror is the missing information, okay? So in the actual calculation, we will say, what we see is how we sample the source. Okay? So if the sampling is not very good, obviously this function is not very good. Okay? Then there's error. You have to correct for it. So you have to correct for the error, correct for the sampling, then you can get the actual picture. So this idea got the Nobel Prize, right? And then we do very clever things, we actually measure things with respect to a large telescope. We have more accurate measurement. Then this is before we correct for the problem error. This is after we correct, okay? So this is the response function as a function of space, you can see after correction, the image will be much better because we have a much cleaner response. We get rid of these little things, error pattern underneath, and squeeze the power back into the middle, then you can get a better picture. Okay, that's called phase referencing. But the magic is this was the original picture that we first get when we make the map, and then this is the answer, right? So everybody would say, that looks like magic. How do you get that? Well, you need a Nobel Prize to do that. Anyway, we have many teams organized to use different types of processing of the data, okay? Independently handling the data with different software. And you can see the answer is more or less the same. The answer looks like a ring, right? But actually it looks like a crescent with one side brighter. It's definitely not a filled disk. It's definitely not 2 points, right? So the answer is something like this. That's what we get, okay? So what does that something we get means, right? So first of all, over time, it's pretty stable. On 3 days, the image we get is roughly the same. So that's good. It says that the longest baseline is going to be very important. And then, this was in the proposal. This is what we get. So I would say the proposal wasn't too bad, except we have the orientation wrong. Why is the orientation wrong? Well, we didn't know what the orientation was, right? But what does the orientation tell us, right? Okay, again, it's a black, looks like a hole. But these are the things that we know, okay? With the photon ring of that size, we calculate the Schwarzschild radius. If it is 5 times the event horizon, it comes out the mass is that 6.5 billion solar masses. That's what is seen in the stellar motion. Okay? So that says all the things that they see in the stellar motion is in that one little pixel, in that black hole. All the mass is packed in there. All of that consistent with a supermassive black hole with that size with the photon ring. Brightness we can actually calculate and actually tells us something about accretion rate. The ring of symmetry is actually the Doppler motion. Okay? The bottom part is the disk that's approaching to you. The top part is the portion that's away from you. That's why the bottom part is a little bit warmer than the top part. Okay? So that also says the disk has to be tipped. If the disk is not tipped, then it goes around like this towards you, no difference. If the disk is tipped, then the bottom part coming at you and the first part going away from you gives the difference. So that tells us that it has to be tipped. Then it tells us the spin, okay? Because the direction of motion will tell us that the spin of the black hole is pointed away from us. So that's a mistake in the proposal. We didn't know which way the spin would point. But I say that's a good mistake. Not so bad. So how do you interpret this? The interpretation is that if you have stuff falling onto a black hole, okay, it doesn't really matter what the outside is doing. By the time it gets to the middle, it has to enforce the motion of the black hole. The black hole will force the stuff to spin in the direction of the black hole. Right? Because it's so strong, it's just going to drag the stuff in while it's rotating. Okay? So the spin of this stuff right near the black hole determines the spin of the black hole. Okay? So if the spin of the black hole is this way, then it's brighter on the bottom. If the spin of the black hole is this way, it will be brighter on the top. That's why we know that the spin is away from us. The right-hand rule. Okay, so what do the stimulation shows? Simulation shows this is calculating the Doppler effect. Okay, so you can put in the simulation. You have this rotating stuff, and then you say, what is it going to look like? Here is actually the orientation of the disk. Okay, you can see when the disk is tilted, one part is brighter. When the disk is face on, the image is evenly bright, right? That's the calculation that shows the Doppler boosting. Okay? When one side is in a disk facing towards you, you will get the brighter side of one side. That's the actual calculation. And then here's the model, and here's the observation, right? Why because our resolution is lousy. When you actually convolve the image without resolution, the image becomes blurry and closer. That's the end result that we get, right? It's the observation. See that? That's just the smoothing because we do not have enough resolution. Okay. Okay, since that time, of course, we start to work on the Milky Way Galaxy. The experiment actually at the same time executed on M87 in 2017. The galactic center is 2,000 times closer, 2,000 times less mass. This is the work where the Nobel Prize was done, except that we are going to look 1,000 times closer to the galactic center. Remember where the star is approaching the black hole? We are actually going even closer by 1,000 times. You take a picture, you verify the general relativity directly on the distortion of space, right? So the question is, what did the galactic center look like? This was the result from the press release. 2022. Looking at the galactic center, getting closer and closer. You see the splashy supernova. Closer, you see this ring, which is the supernova. This spiral of stuff moving in. You see the point, which is the galactic center. Get closer, 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 closer. There. It looks like what we saw. Okay. So, in the galactic center, in the optical, very dark because of dust. In the radio, you can see it high resolution until we see the ring. Okay, so you might ask at this point, what took us so long to make this result? Right, this ring result. This is a second black hole that we can image. It does look like a donut, has a ring-like structure. It is the same source as the Sagittarius star, where the orbital motion for the Nobel Prize was done. Its size scale is 50 microarcsecond, the ring size. From that, again, what is that size scale? Size scale is about the size of a donut on the moon. That's how much resolution you have to have. You have to be able to see a donut on the moon, right? So comparing the two, the physical size is actually much smaller. This ring is 60 million kilometers, right? But this thing is 100 billion kilometers in size. But because of distance, it comes out to be the same angular size, right? Same angular size, just because this is much closer, I told you before. And again, we do all the modeling and show what the reconstruction looks like. Now, the difficulty of this source is that the galactic center is actually rotating on the scale of minutes. So while we're taking the picture over hours, the source is actually rotating. That's why it was very difficult to make this picture, because we did not know how to add one frame to the next frame to the next frame. M87 was much bigger, so it rotated much slower. So picture day after day after day look the same, so we could just add, right, and get the answer. So this one is more difficult, but on the other hand, it means that in the future, with a little bit more sensitivity, we'll be able to make a movie and actually show the rotation, okay, of the black hole. Okay, these are all the people who worked on it. And then, again, the answer summary depends on resolution. Gravitational wave is talking about coalescence of black holes. Optical interferometry, infrared interferometry looks at the motion around the event horizon. And our experiment is actually probe the structure at the event horizon and to test the GR effects, okay? Next generation experiment clearly will have more resolution, more sensitivity. And we intend to continue to help lead this program, and we want Indonesia to be working with us on this. What is the backstory on this? Is that this experiment took us a long time, right? Fred Lowe, which I mentioned, first proposed that the galactic center could have a black hole. And in IAA, we started the
preparatory office about 30 years ago. Okay? And then we developed the instruments, and eventually we joined ALMA, we built SMA, and then we began to build up the VLBI. So this experiment also took us an extremely long time to prepare. Okay? And to do that, such an experiment, we actually need a lot of things. What can I tell you? There are more experiments I cannot tell you right now. It's all embargo. Okay? There's some really nice results on M87 that in Nature at the moment, and next time I come, I'll tell you about those. And then also other experiments that we're doing, which will be very important. Next step. Okay, now I'm gonna have 1 minute. Next step is to build what we've been doing is build the Greenland telescope in addition to what we've been operating. So far the interferometer has been these telescopes. So now we want to add the Greenland telescope in Greenland to achieve even longer baseline. Okay, in the north, and this is here in Greenland. The telescope at the moment is on the west coast, and we're trying to move up there to the center of the Greenland before it melts. This experiment is to recover what we have invested in ALMA in Taiwan, extend the capabilities of ALMA. We recover the prototype antenna in order to build a new antenna, and we want to achieve the shortest wavelength, longest baseline in order to increase the resolution. So this project began in 2009. Here we are shipping the telescope to Greenland. I'm actually standing on the boat over here watching them do this. The reason is that I had to take a boat to move this at the naval base because the base was closed off for fear of terrorism. I had to deliver this telescope by boat from a warehouse to the boat. And it cost, I forget, $50,000. You know, I just couldn't understand why I'm paying so much money going 2 kilometers in the water, right? I thought, are they gonna drop it? But we get there. You know, we reassembled. It was very fast. You know, we were there in 2016. In 2017, we completed. You can see we're clearly at the North Pole. This is just reassembling all the telescope parts. Where am I? Here, you can see clearly it's the North Pole, right, from the stellar tracks. And you can see that it's a snowy area. We do get snow on the telescope. And very famous people start to show up to look at our telescope, including Neil deGrasse. As I said, you should invite Neil deGrasse to come to Indonesia to help in the planetarium work. He's very interested in what we do. And this one is the Denmark Prime Minister. This was the Secretary of the US Air Force, which is very important from the American side. The most important is this guy, because he was Game of Thrones. Everybody was excited about his visit. Not so excited about the other guys, but our staff was really excited when he showed up. Okay, so at the moment, this is what we have. Okay, 9 pixels on the image. We intend to make 225 pixels by working at the top of the mountain at a shorter wavelength. And when that happens, something like this, which we project would be M31 in Andromeda, now we can see the black hole shadow if there is one in M31. Okay? But you couldn't see that if it were this resolution. So the purpose of the experiment is to expand the volume that we can study this and also increase the resolution that we can do this. Okay, so finally, behind excellence, you need to develop new technology in order to do things. Typically, you have to improve by big factors, like 1,000 times, right? Can Taiwan work at the frontier that we show is yes, so Asia can also do the same. How to do the right problem, you have to find the right people. How to find the right people, you have to work at the frontier. If you're not working at the most exciting things, you're not going to find the best people to work on it. Why? Because the best people will want to work on the best stuff. And then how do you find enough resources? You need a godfather or godmother. Do it by yourself. Right? How to find the right directions,
always new directions. What's the key to success? Persistence. You have to keep doing it. You cannot be discouraged and give up. Guiding principle, always think the future will always be better. That's why we work, for the better future, right? So in this case, in Taiwan, we depend on our academy president. That's why yesterday I saw your academy president, because I think you need a godfather like we did. And it takes a long time. This young man lost all his hair. Very distinguished looking after 30 years. He wrote this nice book on how to catch the black hole. And then finally, I want to come to this about teamwork, right? You can never tell where you fall. In my case, it all started with the donut. I think it was just a donut, right? But the deep meaning of the donut was there from 50 years ago. Okay, now for you guys in Indonesia, we would like you to join and step up your activity in radio, because radio is a very important window. It looks at cold matter, cold dust. We can measure magnetic field. We can look at distant galaxies because the redshifts. This is another talk some other day. JCMT is part of the Earth-sized telescope, the Event Horizon Telescope. Indonesia already is observer status, which means that you can participate in all these experiments. EHC experiments, the telescope single dish experiments, large programs. All you need to do is tell me you want to work on it, right? So it's very straightforward. Why do we do this? It's because we are trying to build a future. We have to do it together. Today we have 4 organizations originally, but Thailand has joined in 2021. Malaysia is aiming to join. India is working on it. And we would like Indonesia to also join. And the future is to join a treaty organization for astronomy. We're working on that in order to become a very large cooperation. Why do we do that? Because we need to compete with the rest of the world. What are we competing for? We are competing for you. We don't want you to disappear into North America or Europe. We want you to train, but we want you to come back. We want you to build the future for Indonesia. We want you to build the future for Asia. That's why I'm working on this, right? To try to get you guys to do it. Why do we do it? It's because the economics tells us this is the future. Okay? This is GDP today. You can see in our region, we already have similar GDP as all of Europe. Just these 3 countries. Okay? But by 2050, just these countries will overwhelm what Europe's GDP will be by a large factor. Okay? And today, even though the amount of GDP is the same, the amount invested in astronomy is very small compared to what the rest of the world is doing. So in Asia, we could do a lot more just based on our current economic power. Okay? And where is Indonesia's role? Okay? This is comparing the GDP 2018, 2021, 2026. Predicted growth rate is about 50%. Right? You see that Southeast Asia is all about 50%. The developed region, like Japan, is 2%. Right? Korea, Taiwan, they're slowing down. East Asia is growing. Why? Because of the population, right? The amount of money that we're talking about, 1% of ESO, which is where we are at now, is about 10 to the minus 7 GDP. So if you calculate the GDP, 10 to the minus 7, we need about $100,000 from at the moment, right? So, my invitation is that from observer status, we hope you become associate partner or full partner. What is the difference? Associate partner, just go ahead and do the science, radio astronomy, optical astronomy, putting the staff at the observatory. But if you become full partner, then we are planning the future together. We're building together. We're building the next instrument together. We're building the next mega project. Okay? Of course, this budget will come up but this is a matter to discuss how fast we grow. Okay, but the point is that Indonesia has a very large economy. Your government is sitting on a very large GDP. The usual figure of merit for science research is 3 to 5% of your GDP should be devoted to R&D. Reason? That is your future. If you don't invest in that R&D, we will always be just manufacturing something for somebody else. We'll just be factories, okay? You cannot do that into the future. We need to invest, right? What do you invest? This is one possible example. Okay, I stop there.